Our first 3-minute thesis finalist is Cansu Duzgun from the Department of Earth, Ocean, and Atmospheric Science. The presentation title is Revisiting a Legacy Theory of How Clouds Breathe Using Machine Learning.
Weather models become so reliable that when you ask a friend about the weather, she might check her phone instead of just looking outside. We all trust our weather apps for short-term forecasts. If it says heavy rain in 30 minutes, we just grab an umbrella. But what if the forecast is for 3 or 4 days later? Here in Florida, when there is a possible hurricane heading toward Tallahassee, we don't make immediate decisions based on those forecasts. Because the further we look into the future, the more uncertain weather forecasts become. Weather models built by humans, and there are still some atmospheric processes that we don't fully understand. One of those processes is how dry environmental air mixes into cloud. As meteorologists, we call this process as entrainment. But let's just call it as cloud mixing to avoid terminology here. Cloud mixing determines how thunderstorm clouds grow, how tall they become, how much rain they produce, or how severe they can be. In other words, how clouds breathe determines their potential hazard. The problem is that the way that we represent cloud mixing in today's weather models is based on a laboratory water tank experiment from 1965. Scientists at that time thought that the upside-down view of it resembles how thunderstorm clouds look, and I think that's very clever. This legacy theory works reasonably well for short-term forecasts, but its simplifications introduces systematic biases that becomes especially important for long-term weather and climate simulations, which run for decades, not for days. In my PhD research, instead of relying this experiment only, I brought together modern satellite, radar, and atmospheric data to build nearly global dataset with many thunderstorm cases. I then used machine learning, not as a black box, but as a tool to uncover hidden, nonlinear relationships of cloud mixing and its surrounding environment. By combining modern observations with interpretable AI, my research strengthens and refines a foundational theory of cloud physics. And ultimately, this will help weather and climate simulations better represent how clouds breathe, so in that we can plan for risk, resilience, and extreme weather with confidence. This research is a testament to what we can achieve when we harness the power of AI and machine learning for the good of our planet.